Hello, my name is Farid Konduri and I work as Tools Lead in Advanced Safety Aptiv Sweden. Today I would like to share the result of the project we conducted to understand the challenges and opportunities when employing simulation environments for sensing performance evaluation. Let me start by introducing Aptiv. At Aptiv, we are a global technology company that develops safer, greener, and more connected solutions, which enable the future of mobility and help address some of our customers' toughest challenges. Our portfolio comprises both the brain and nervous system of the vehicle that is underscored by core capabilities which span across four key areas: power, data, compute, and software. These foundational capabilities allow us to deliver optimized solutions for active safety, high voltage electrification, and connectivity. By working deeply with many customers globally, as well as Motional, our joint venture for autonomous driving with Hyundai, we have gained a deep understanding of the technology challenges. Today's presentation will focus on a very specific aspect of those challenges, which is how do we tackle the problem of verification and validation of autonomous vehicles through synthetic data generated in simulation environments. We see continued acceleration of these safe, green, and connected technologies. Active safety, shown here, is just one example. For Aptiv, we help our customers thrive in this environment by acting as a trusted technology partner that empowers this transition. For leading OEMs, we can act as co-creation partner, helping to solve their toughest challenges, as we have a long track record of creating and integrating these complex solutions. Then, as those solutions mature, we find ways to optimize it, helping democratize the technology or make it mainstream. Having the strong demand for increased functionality in advanced safety capabilities, it is really crucial for us to ensure verification and validation of such systems. Right now, the main approach for test and verification of advanced safety systems is brute force validation. A fleet of test cars are used to drive on public roads and test tracks to collect data and analyze the system performance. This method, however, this method has its own limitations. It is very expensive, time-consuming, and also potentially dangerous. Besides this limitation, growing complexity of such advanced systems, as well as more strict requirements, lead us to consider other methods that complement field test data and improve the situation. And that brings us to consider simulation environments where we can save time and effort by utilizing such environments for verification and validation of advanced safety solution. As you may know, simulation environments are flexible, so you can change world model parameters and modify sensor models in different scenarios. You can change weather, road type, illumination. So it gives you this flexibility. It is also efficient. It can save us a lot of time through scripting and iterating through the scenarios. And it is inexpensive compared to brute force validation. So it is a really good option for us to consider and use this solution. Now let's see how much simulation environments are utilized in advanced safety work. We can say that advanced safety systems try to solve two main technical problems. First, sensing, where we use different sensors like radars, cameras, and lidars to make the car see and understand the world and its surrounding and detect and classify objects. That is sensing or perception. And then planning, where we try to teach the car how to handle chaotic situations where human level negotiations are needed, like one sample as shown here. Now let's imagine we have a scale that indicates simulation environment utilization in advanced safety with respect to these two blocks from left to right from 100 to 0. So let's see what we can see using this scale. So we see that currently sensing block is not really gaining from simulation tools compared to the other block, planning, where many developers take the advantage of simulation tools to test and verify their functions. So then we might wonder, we might ask ourselves this question: why is it that sensing is not gaining from simulation tools compared to the planning? When you think of it, you should think of the different nature of sensing block, and you may wonder whether or not simulation environments are suitable for sensing algorithm or for the sensing block. Therefore, you can come to the key question that does simulation environment represent the reality sufficiently good and bad for sensing algorithm? And that was the main question that we tried to address. And I think everyone in the industry, in this community, should also consider and think about it. Having that key question in mind, we started a project to understand the similarities and correlations between real and synthetic data. We aimed for a closed-loop simulation to evaluate performance of our sensing algorithms and compare it to the real-world data. In the simulation environment, we have a world model where inside that there is target, illumination, weather, and also ego vehicle, so we can model those items. And then sensor model, in our case, it's only camera or vision sensor. And inside camera model, we have a lens and imager. So out of this environment, synthetic data is created and generated and sent to active environment, where we use our tool chain to process this synthetic data. So we have our own sensor processing seal block where our algorithm processes the synthetic data and generates some detections, some objects like traffic sign, lanes, objects, car. And then those detections are fed to the next block, feature functions, where some functionalities are implemented like automatic braking, ACC, or a lane keeping assist, and then we close the loop. So we get the closed-loop simulation. So remember that the aim was to really see the similarities and analyze the sensor performance algorithms. So for that, we also use the data that we have already collected in our projects from public roads and from test tracks, and then we use that data and inject it to the seal, and then try to compare and analyze the sensor sensing performance with respect to these two type of data. So that's what we did in this project. So from simulation environment and modeling, it was very important for us to have a camera model as close as possible to the reality. So starting from the raw image created in the simulation environment, we use different filters to degrade the image. Different filters are used to introduce distortion, blurriness, vignetting, to get the image as close as possible to the reality. And then the image is converted to a grayscale one to be ready to be processed by our algorithm. So you see that from that shiny high resolution image on the left, we end up using the grayscale noisy distorted image on the right. And that's kind of the data that sensing needs. It doesn't need a perfect data. It's also good to mention that we perform another set of tests, which are specifically designed to measure the optical performance of our lens model. So with doing that, we ensure that the lens and eventually the camera model that we have in simulation environment, they are modeled as close as possible to the reality. So they are close to the ones that we already use in our production. So using this camera model and generating the data which are suitable and proper and ready to be processed. So I want to show you the next slide where we kind of recreate these real scenarios in simulation environment. On the right, you see the real world data. On the left is simulation environment when we try to mimic the reality. So I go to the next video, and recreating these scenarios in simulation environment, we try to see what is the performance of sensor. So you see the red box around the target car. So that is the output from our, that's a detection from our sensors. And in our tool chain, we log this data to analyze and compare the performance in these two different environments. So now let me go to the next slide when I can show you the result of the sensing performance evaluation. So on the right, you see the table that shows 12 test cases and their results from real data and synthetic data. And as you can see, 10 cases are matching and are similar performance. We see similarity between 10 cases, and only 2 cases are not similar, 2 red ones. We also see significant correlation in signal behaviors between synthetic and real data. On the left, there's a sample plot that shows some of the signals that are important for our sensing algorithm that are plotted here, and you see the very close behavior and correlation between these two data. Now, let me share some remarks, lessons that we learned from this project. First, when you think of simulation environments, note that synthetic data can be used for complementing field test data, replacing it. So we are not going to remove or leave the real data, or field test data, but we want to improve the situation with simulation tools with synthetic data. So definitely we need real data. Second, there is a misconception that synthetic data is too easy or let's say too biased for the sensing algorithms to be detected. And but what we saw was that it's not the case, and synthetic data can really challenge the algorithm. And it was shown. It was shown in the table that I shared with you. Finally, getting back to our main question and trying to see if we can answer it. Does simulation environment represent reality? We can't really answer this question, as we believe more investigation is needed. Of course, what we got in the project was really promising, and however, it is not conclusive. We got 83% or 10 out of 12 test case matches, 10 out of 12 test case matching. And we also saw significant overlap in signal behaviors, but still more investigations are needed to prove the potential of such simulation tools. It's not enough. Finally, I would like to share some high-level challenges that as an industry we all need to join forces and work together and collaborate to address these challenges. First is the reliability of KPI measurements on synthetic data. We see that some people don't trust these environments, synthetic data and simulation tools, and this really needs to be addressed. If no one is going to trust this data, so there's no gain or no value here doing investing on simulation tools. And I really believe doing studies, investigations, and research similar to what I shared today with you will help us to address this challenge and uncover the potential of the simulation environment. The second challenge is the need for open and transparent collaboration between different actors in the industry. We all in this community, including vehicle manufacturers, sensor developers, simulation and sensor model providers, as well as proving grounds, we all need to collaborate and contribute and help each other. We need to share data. We need to share our vehicle models, sensor models, and ground truth data from test tracks to enable this and to address the challenges. And And last but not least, enabling co-simulation possibility across various simulation environments. We see the tendency in our customers that they want to have their own simulation tools, sensor models, but sometimes it is not really easy to co-simulate and think this different environment to integrate sensor models. So it's really hard to make to integrate these environments and to make them talk to each other and get sync. So instead of developing new tools, we should enable co-simulation between this simulation environment and think of interfaces or standards that enable this. Having said that, I would like to thank you for listening to my presentation, and please feel free to ask questions. Thank you. Bye.